A fury is building on the surface of the sun. Jets of super-hot gas, towering waves of fire, the most violent explosions in our solar system. Science is now taking us on an extraordinary journey into our star. To explore the power and rising threat of solar superstorms. We think of the sun as a constant, a tranquil vision eternal. And yet, beneath the calm, a storm is gathering force. It's September 1st, the year 1859. The English astronomer Richard Carrington notes signs of turbulence rising across the surface of our star. It's the beginning of one of the most violent solar outbursts on record. Searing jets fall tens of thousands of kilometers into space. Vast roiling towers of super-hot gas billow upward. Temperatures soar to millions of degrees Celsius. Amid the turmoil, a strange dark region appears. A cluster of sunspots, now estimated to have been 20 times the size of Earth. From this region, the sun erupts in what scientists call a coronal mass ejection. Over 1 billion tons of solar particles head in our direction. Based on the timing of Carrington's observations, scientists now estimate that the solar blast traveled at over 8 million kilometers per hour. Observers around the world greeted its arrival as day dissolved to night. Solar particles excited oxygen and nitrogen molecules in the upper atmosphere, turning the night aglow. The northern and southern lights are usually visible only at the poles. That night, they stretched all the way to the tropics. Watching from a campsite in the Colorado Rockies, a journalist described an auroral light so bright that one could easily read common print. An observer in Havana, Cuba, reported that the sky appeared stained with blood and in a state of general conflagration. In New York City, thousands gathered on sidewalks and rooftops to watch the glowing skies. But the spectacle had a dark side. In those days, telegraph networks were taking hold as an efficient new means of long-distance communication. Transcontinental and transatlantic lines were in the works. Through the week, British instruments recorded wild swings in geomagnetic activity. Electricity began to surge through telegraph wires. Some operators found they could turn their batteries off and still transmit. Others received shocks. Transformers blew. Had Earth been hit by some form of meteoric matter? Was it a form of high-altitude lightning, never before seen? To scientists, the culprit was soon clear. It was the sun and associated forces of electricity and magnetism. It was our first warning that our star can threaten the way we live and communicate. A modern-day wake-up call came in March 1989. A solar outburst took down Canada's Hydro-Quebec power grid, leaving 6 million people without electricity for up to 9 hours. Another came in 2003, with Halloween approaching. It had been 3.5 years since the sun last erupted in fury, at the peak of an 11-year cycle of solar flare-ups. Sunspots appeared unexpectedly. Over a period of 2.5 weeks, scientists recorded 17 solar outbursts, including the largest emission of solar X-rays ever seen. Slamming into Earth's upper atmosphere, solar particles damaged 28 communication satellites and destroyed 2. A newly installed GPS-based air navigation system went down for 30 hours. Here is the sequence of eruptions, courtesy of the newly launched Solar and Heliospheric Observatory, or SOHO. The Halloween storms did not stop at Earth. Sweeping past Mars, the solar blast was so strong that it burned out the radiation monitor aboard the spacecraft Mars Global Surveyor. Ironically, this instrument was designed to study radiation that human explorers might encounter on future missions beyond Earth. The same pulse of solar energy was recorded by the two Voyager spacecraft on their way to the far reaches of the solar system. While solar storms are not dangerous to people, they can pose a significant threat to our increasingly power and technology-dependent world. A recent estimate published by the National Academy of Sciences held that an outburst like the one in 1859 could cause damage of $1 to $2 trillion in the first year alone, rivaling the cost of the worst hurricanes or earthquakes. The risk starts with the fleet of satellites that orbit the Earth. As well as the sprawling complex of air travel, dependent on satellite GPS navigation. It extends to a vast network of electronic, phone, and internet wires that knit together and define modern life. It's not only the cost of repairing and replacing damaged components, but the loss of business and government services extending over the years it takes to recover. The problem is not limited to higher latitudes. Scientists have found that solar plasma can amplify a band of electrical current that orbits the Earth, snaking its way above equatorial regions. This equatorial electrojet can provoke spikes of electrical current on the ground, posing risks to electrical grids that may not be set up to handle them. The more integrated and global our technological infrastructure becomes, the more vulnerable it is. This realization has led scientists in the last 2 decades to launch a fleet of new generation spacecraft designed to closely monitor the Sun. They've taken up positions in low Earth orbit to measure incoming solar particles and their interaction with our atmosphere. And they are circling out in interplanetary space to track solar activity in unprecedented detail. These spacecraft are documenting solar activity in wavelengths up and down the electromagnetic spectrum. With all this data flowing in, scientists are drawing an increasingly complex picture of the Sun and its inner workings. Their aim is to predict solar eruptions more accurately than ever before, and to usher in a whole new era in space weather forecasting. This effort includes a powerful new tool. Supercomputer programs, or models, that use the laws of physics to simulate the workings of the universe, including stars like our Sun. To understand the source of the Sun's power, we peer into this virtual telescope and look back to the early moments of cosmic history. Within the first 300 million years, gravity drew the primordial gas into filaments and dense centers. The first generation of stars ignited. Trillions upon trillions of newborn stars flooded the cosmos with intense ultraviolet light that heated their surroundings. Vast patches of hot gas intersected and merged. The largest stars spread additional heat and radiation by exploding in supernovas. This outpouring of energy changed the character of the universe, down to the smallest of scales. It stripped electrons away from hydrogen atoms, turning nearly all matter in the universe into the ultimate cosmic elixir, an electrified gas known as plasma. On our planet, plasma can be found wherever temperatures rise to extremes. From the red-hot core of a flame to the white-hot flash of a lightning bolt. We create plasma by sending electric currents into a gas such as neon. That frees electrons from nuclei and excites them, causing the gas to glow. In space, plasma too is electrically charged. As a result, when matter moves or swirls around under the influence of gravity, it generates a strange driving force, magnetism. Magnetic fields can channel or even block the flow of plasma. You can see this on a large scale in the famed M51 galaxy. Plasma swirling around this spiral galaxy has generated a network of magnetic fields, shown in this map. These fields carry matter away from the plane of the galaxy. In doing so, they sap energy from its rotating motion, allowing gas to fall toward the center. There is a similar dynamic at work deep in the center of some galaxies. Plasma drawn by the gravitational pull of a supermassive black hole forms a spinning disk. It generates magnetic fields that spiral up and out. They channel a portion of the inflowing plasma into jets so powerful they approach the speed of light. Astronomers have spotted ultra-high-speed jets shooting out of many a large galaxy. In the case of NGC 1275, magnetic fields generated by a central black hole suspend an intricate network of gas filaments above the galaxy. In our own neck of the woods, the dynamic properties of plasma account for the energy we see rippling across the surface of our star. NASA's orbiting telescope, the Solar Dynamics Observatory, has given us an extraordinary view of a wide variety of phenomena. From fiery jets and massive white-hot flares to dazzling loops that rise into the sun's atmosphere. To understand how solar plasma can fuel an eruption on the scale of 1859, the so-called Carrington event, we must travel deep below its surface. In the sun's core is a nuclear furnace heated to 15 million degrees Celsius. The pressure and the heat rise, causing a fusion reaction in which hydrogen atoms crash together, merging to form heavier atoms like helium. These fusion reactions give off heat, which rises in plumes to the surface of the sun, on a journey that can last tens of millions of years. Scientists have been using supercomputer models to simulate this journey. They have found that as the flow of plasma reaches the sun's outer layer, the convective zone, it breaks down into complex swirls and loops. Near the equator, where the sun rotates quickly, it forms vast rolling waves. Because plasma is made up of electrically charged particles, these churning motions produce magnetic fields, shown here in blue. They thread through the sun's outer layers like vast rivers of energy. If the energy in these fields is strong enough, they may twist or snap, then spiral upward. This computer model takes us just below the surface. As the magnetic field pushes through this hellish region, it forms immense rising arcs. They become enveloped in electrical currents, the cloud-like features shown here. These currents, generated by rising and sinking streams of plasma, pump energy into the magnetic arcs. As the arcs stretch upward, they can draw huge volumes of hot plasma toward the surface. Where they burst into the solar atmosphere, they form so-called active regions. You can't actually see the magnetic loops, but you can see plasma coursing through them, rising up one side and draining down the other. At times, if these fields transport enough energy to the surface, they can fuel magnificent jets called prominences. Covering an even larger area, active regions can burst forth in white-hot solar flares that release the energy of over 1 million hydrogen bombs. But the magnetic fields that spur this energy release can also stifle it. As a result, active regions are often flanked by sunspots, where surface temperatures can drop by as much as 2,000 degrees Celsius. 4 centuries ago, Galileo Galilei was the first to argue that these blotches were actually on the sun's surface, though he suspected they were clouds. Their nature remained unclear until 1908, when astronomer George Ellery Hale demonstrated the link between sunspots and intense magnetic fields. When a cluster of sunspots appears, it's a sign that magnetic energy is building below the surface to staggering levels. This view, captured by the Hinode satellite, shows energy escaping from the vicinity of a sunspot in wavy, grass-like structures called spicules. At temperatures in the millions of degrees, these short-lived jets are thought to be one reason the solar atmosphere is so much hotter than the visible surface. In this sequence, you can see a solar flare erupting among a cluster of sunspots. This energy release can take on added power if the sunspots rotate like vast hurricanes under the influence of the sun's own spinning motions. The magnetic fields begin to twist around and the energy within them to rise. These spinning motions have been linked to the largest solar eruptions of all: coronal mass ejections. A goal of solar astronomy is to catch events like this from multiple angles and in multiple wavelengths, as seen in this composite of different telescope views. That effort paid off in July 2012, when the Solar Dynamics Observatory captured a flare in the making on the visible edge or limb of the sun. One of its sensors, designed to record events at 10 million degrees, allowed scientists to peer into a tangle of rising arcs. By adding data from the Stereo A spacecraft, they were able to create a 3D picture of figure-8 patterns in the rising arcs. This twisting configuration preceded the eruption, captured here by the Solar Dynamics Observatory. The event continued to dazzle as plasma flowed up into magnetic arcs and down in what's been called a coronal rain. Coronal mass ejections are huge bubbles of gas threaded through with magnetic field lines. They are part of a larger flow of energy from the Sun, including a constant stream of particles called the solar wind. It can travel to the far corners of the solar system, causing even distant Saturn to light up in colorful auroras. To understand what a powerful force this solar flow can be, take a look at Earth's sister planet, Venus. The European spacecraft, Venus Express, recently found that solar winds are steadily stripping off lighter water molecules in its upper atmosphere, sending them flowing away from the planet's night side. Over the eons, what's left in Venus's atmosphere is a witch's brew of acetic gases and carbon dioxide. Looking at Venus from orbit, you'd see a dense layer of high-altitude clouds from 45 to 66 kilometers above the surface. These clouds are so dense and reflective that Venus absorbs much less solar energy than Earth, even though it's 30% closer to the Sun. And yet, down on its surface, Venus is like a house on fire, with its windows forever closed. Venus is in the grips of a runaway greenhouse effect, with an atmosphere that traps increasing amounts of solar energy. Temperatures hover at 464 degrees Celsius, hot enough to melt lead. Air pressures are 90 times higher than at sea level on Earth. At higher elevations, a fine mist forms, not of water, but of the rare metal tellurium and iron pyrites, known on Earth as fool's gold. It can form a metallic frost, like snowflakes in hell. The surface is pocked with volcanic formations, ranging from lava domes to large eruptive summits. With water unable to take hold here, these formations continually replenish the noxious atmosphere. How did Earth avoid such a harsh fate? When a solar blast moves out into space, it extends well above and below the orbits of the planets. Sweeping by Venus, it takes aim at our planet. When it hits, the blast slams into a kind of protective shield, one that Venus lacks. Earth's spin causes molten iron circulating deep in its core to generate magnetic fields. They extend beyond our atmosphere, enveloping the Earth in what's called the magnetosphere. It diverts most of the incoming solar particles past the Earth. While Earth's magnetic field may be strong, it does not shield us from the worst solar eruptions. This supercomputer model was created by scientists to understand the events that can trigger a coronal mass ejection on the scale of 1859. It shows magnetic arcs rising hundreds of thousands of kilometers above the surface, a sign that electrical energy is coursing through them. When this energy reaches a critical threshold, the arcs become unstable. They unravel, suddenly and violently, in a coronal mass ejection. This has the effect of clearing a hole in the solar atmosphere. If the arcs reform, a second eruption moves out with even greater force and speed. The Great Solar Storm of 1859 actually hit Earth in several powerful pulses. The first one produced bright auroras on Sunday, August 28th. A second, more energetic blast struck the following Thursday. We got a taste of how powerful such an event can be in July 2012. The NASA Stereo A spacecraft recorded two small coronal mass ejections, followed by a Carrington scale blast. Had this event occurred a week earlier, it might have hit us, with catastrophic effects. Scientists used it as a test case for understanding the behavior of Earth's magnetosphere under a powerful solar onslaught. A computer model shows a normal day. The solar wind flows continuously past the Earth, distorting its magnetic field and pulling it around the back in a tail-like structure. A typical coronal mass ejection pushes Earth's field in and lengthens its tail. The magnetosphere remains largely intact. A Carrington scale event is a different story. It severely compresses Earth's magnetic field while packing the boundary with plasma. To find out how this plasma actually reaches Earth, scientists have simulated its approach in one of the largest solar computer models ever produced. The solar plasma heads toward our planet aboard streams of magnetic field, shown in blue. On its leading edge, where it pushes up against Earth's magnetic field, turbulence develops. Cracks begin to open up in Earth's protective armor. The fissures widen. Millions of tons of electrified gas now surge through in jet-like flows that can engulf the planet. No one knows exactly why, but solar magnetic activity rises and falls in a cycle that lasts about 11 years. At the peak of this cycle, the Sun can churn out as many as 3 coronal mass ejections in a day. They grace us with spectacles of color and light, beautiful beyond measure. They are a reminder of the intimate connection between our planet and our star. When auroras crown our atmosphere, they may stretch hundreds of kilometers into space. Imagine being able to see them spread far and wide before you, like astronauts can aboard the International Space Station. The station was built to protect them from solar radiation. They are safe as long as they stay inside. Lately, thanks to high-resolution digital cameras, astronauts have allowed us to share the view out their windows. As solar plasma reaches across the void to paint our skies in greens and blues and reds. Today, scientists are keeping a close watch on solar activity while working to improve forecast models. With enough advance warning, airplanes can be diverted away from the poles. Satellites can be powered down or turned away from onrushing solar plasma. On the ground, power grids can be protected by temporarily shutting them down. Meanwhile, scientists are racing to add another line of defense: knowledge of how and when the sun can threaten us. Solar storms like the one documented by Richard Carrington in 1859 are thought to hit Earth about every 150 years. At that rate, we may be due for another. With every violent eruption, the sun relinquishes another clue and another warning. To brace ourselves for the next solar superstorm.